All right, we're going to continue our theorem gauntlet and probably end it now, and then we'll be done with the chapter. Let's take stock of where we're at. We've just proven that if you have two roots of the same irreducible polynomial, then there's an isomorphism that takes one field extension to the other, which extends the identity. Now let's look at a slightly more complicated situation where we have the following setup. Sorry, I was scrolled down there. We have a field F, two extensions, K1 and K2 of F, and E extends them both. So the picture kind of looks like this. Now, we've seen this kind of situation before. We're going to add one more piece of information, which is that we will add in an isomorphism H. I don't know that I should put that arrow in the picture because these arrows are showing containments, and this is a map. So let me just write HK1 to K2 is an isomorphism. And we'll assume that H fixes F. So what that means is we are saying that H extends the identity on F. In other words, H of X equals X for every X in F. Now, suppose that I take some element of K, K1, let's call it C. Since it lives in this K1, it's a field extension, I can write it as a root of some polynomial, right? I can say that C solves A of X, and maybe that's A0 plus A1X plus A2X squared, and so on, as follows. Now, since this thing is in K1, which is an extension of F, I want this to be happening in F. So these coefficients, all the A's will then live in F. The first piece of magic is that H of C is also a root of A. It also solves A of X. Let's convince ourselves that this is correct. So since we know that A of C equals 0, this is to say that A0 plus A1C plus A2C squared, and so on, up to A and C to the n, all of these things are 0. Or sorry, this equals 0. On the other hand, what is A of H of C? Well, then I just plug H of C in where all the C's are, right? I'm just basically inserting an H because it's a homomorphism, an isomorphism. The squared can live on the outside because it respects multiplication. Now, the magic happens here when we remember that because H fixes F and all of the A's live in F, I can put an H on every single one of these A's for free. You might be thinking, okay, but what's the point of that? Surely you're just adding stuff, right? Well, because this thing respects multiplication, I can combine all of these into one H. And because it respects addition, I can combine them all into one big old H. But you see from the very first part, C solves that polynomial. So H of all this stuff is just 0, right? All this stuff equals 0. And H of 0 equals 0 because it is an isomorphism. So our first little result, very important result. I'm going to put an exclam here because we're going to use this. This is going to be a core insight for later, even though it's not in Pinter promoted to a theorem. Let A of X be a polynomial. In particular, it's a polynomial in f of x. I should actually write down all the assumptions, right? Any isomorphism fixing f sends roots to roots. Now, two comments are in order. The first is we can add a little bit more to the situation. We can add a little bit more clarity and structure to the situation by introducing the concept of a root field. A root field of f is the smallest extension of f containing all the roots a1 through an of some polynomial a of x. E.g., it's of the form k equals f adjoin a1 through an. Pinter uses the C's in his notebook or in his textbook instead, but I don't care. The terminology is not important. When you're in this setup, we have the roots explicitly. And so what this means is these things have to be permuted, right? So maybe this also warrants an exclam, right? Because it's a rephrasing of the previous exclam. The AI get permuted by this isomorphism. Okay, now, previously, there was a technical result in Pinter. He tagged it as for later reference. Trying to remember which result this is. We can go take a quick look. Where is this theorem? Okay, I confess I don't recall where this theorem is, but you guys also have the book. You guys can go look it up. I just wrote down there's a technical reference. What we know is that elements of a field like this, right? We know that what the basis elements are of this thing, right? They're sums of, or sorry, the basis elements are all the products of the individual AIs and their powers. And so what you get is something like a constant C times A1 to some K1 power, A2 to some K2 power, and so on, right? That's what the elements are. These are like, and then there's sums of these things. And the constant, of course, lives in F. H fixes F. H sends a constant to itself. And so since the roots are permuted, these things get all mixed up, right? Their individual monomial powers can be changed. But it's still going to be of that form, right? A sum of doodads like that. In other words, still something that lives in that specific field. So therefore, H sends everything of that form to things of that form. Or in other words, sends the field to itself. This is the essence of Pinter's Theorem 5. So we got K, K prime, finite extensions of F. K is the root field of some polynomial. We could say AX in FX. If H K to K prime is an isomorphism then K is equal to K prime. And we're like 90% of the way to the proof on this already. Let's just scribble out a proof. From the theorem 2, these are simple extensions, right? I can replace the root fields with, I don't know, f of adjoin some alpha, here's some beta. What we know is that E extends them both, right? Where E is f of alpha beta. Because of what we were just talking about, H has to send everything in K to some K prime. And that gets us one containment. On the other hand, the same works in the reverse because the inverse is also an isomorphism. So here, how do I write this? What I want to say is H gives us K is a subset of K prime. H inverse gives a reverse inclusion. So they're equal. All right, let's get our last theorem, our last main theorem done. And then we have two more results for the future that we should just write down. I won't record their proofs. Theorem 6. I know, so many theorems. Theorem 6 says if I have two extensions, L and L prime, finite extensions of F, excuse me, K an extension of L, which is a root field, any isomorphism L to L prime fixing F, can be extended to also fix, can be extended to an isomorphism H, if we'll use the fancy H with the overline K to K. Okay. The proof of this, it's just a couple sentences. From our second theorem in characteristic 0, K is simple, right? So we take K, we write it as L of C. By the first theorem in this video, we extend the isomorphism from H, we have H, L to L prime. We extend that to an isomorphism H bar, L of C, to some L prime of D. But now, because of the previous theorem, we're done, right? The previous theorem says that we can identify K with K prime. So we declare victory. Okay. These have been a whole gauntlet of difficult theorems. And I said I would record these last two theorems. I'm realizing that I've been once again talking now for almost 15 minutes because it's just been quite a lot to unpack here. So I think I'm just going to actually leave that and I mean, Pinter's kind of upfront about this, that these are a little bit technical, even though their proofs are pretty easy. I think we're going to call it here because I feel like there's a 100% chance that we are confused and looking for some clarity on all of this. So what I'm going to do is we're going to stop this here for now, and we're going to do a bunch of examples coming up. And I will try my best to clarify some of these concepts involving root fields in particular, and fixed fields when we can. We'll try to look at some examples both in characteristic 0 and in characteristic P, because I also said that I would try to give you guys a little bit of kind of flavor for what happens in characteristic P. And then I'm hoping that once we've seen how some of the examples work, we will feel a little bit better about all of this, because this concept of fixed field is going to be the main workhorse for next chapter's Galois theory. But we're almost done, right? Just 2 more to go. So bear with me just a little bit longer, and let's see what we make of the following examples.